Hello, this is Victoria Tencio, and this is my submission for exam chapter 23. The first problem states an electron charge negative E, so I'm gonna start writing down all my givens. (1.60 times 10 to the negative 19th columns) is at rest at a distance of 1 times 10 to the negative 10 meters from the center of the nucleus of a nucleus of lead, and it gives us the charge plus 82E is equal to 131 times 10 to the negative 17 columns. You may treat both objects as point charges. How much work would you have to do to move the electron to a distance of 5 times 10 to the negative 10 meters from the center of the lead nucleus? So what we're going to do is utilize the following formula of work. K Q1, Q2 for the charges, charge 1, charge 2, divided by distance number 2 minus K, Q1, Q2, my apologies, over distance 1. So we're gonna solve this, move things around. So we're gonna factor. So this would be K, Q1, Q2 divided by, multiplied by 1 over D2 minus 1 over D1. So then we just plug our values in. Our K is 9 times 10 to the 9th multiplied by our first charge, which is actually this number is negative 1.60 times 10 to the negative 19. Our second charge, which is the 131 times 10 to the negative 17. This is going to be multiplied by 1 distance number 2, 1 over distance number 2, 5 times 10 to the negative 10, minus 1 over D1, which is 1 times 10 to the negative 10. Okay, and then when we plug this into our calculator, we get, let me grab my calculator over here. Times this is 5 this is minus and we get 1.509, which would be 151 times 10 to the negative 12 joules. So that's our answer for part A. Part B states the following. If you release the electron from the position in A, what will be its kinetic energy when it is at distance 8 times 10 to the negative 12 from the center of the lead nucleus. You can assume that the lead nucleus remains at rest since it is much more massive than the electron. So what we're going to do is utilize this formula, KEQ divided by RF, and then basically just plug our numbers in. This would be our charge, 9 times 10 to the 9, multiplied by our first charge times 10 to the negative 19, and our second charge. This would be our two charges together. Same thing, same deal as it was up here. 131 actually. Times 10 to the negative 17. And this is all divided by the new given distance, which is 8 times 10 to the negative 12. And then when we put this in our calculator, we get 8E. We get negative 235.8 times 10 to the negative 17 joules. And then we're gonna get, since we got our UF, we need to get our UY. So then we can solve and get our answer for this part. So basically, I'm gonna do the same thing, 9 times 10. So we have our charge, and then we have 1.60 times 10 to the negative 19 times our new charge, not our new charge, but our separate charge. Okay, our separate charge divided by 1 times 10 to the negative 10. And when we plug this in the calculator, which I already did, we get negative 18.86 times 10 to the negative 17 joules. So what we're going to do is just subtract these two, so the UF minus the UI. This would be the 235 times 10 to the negative 17 minus 18 times 86 times 10 to the negative 17. I don't know why I did a negative here. This should not be negative. Multiplied by 10 to the negative 17. And then we get 216.94 times 10 to the negative 17 joules. And that is our answer for part B. Part C states, in a nuclear physics experiment, a proton with mass 1.67 times 10 to the negative 27 kilograms, charge of E is equal to 1.60 times 10 to the negative 19 coulombs, is fired directly at a target nucleus of unknown charge. You can treat both objects as point charges and assume that the nucleus remains at rest. When it is far from its target, the proton has speed of 2.50 times 10 to the negative 6 meters per second. The proton comes momentarily to rest at a distance of 5.29 times 10 to the negative 13 meters from the center of the target nucleus, then flies back in the direction from which it came. What is the electric potential energy of the proton and nucleus when they are 5.29 times 10 to the negative 13 meters apart? So the way that we're going to start this is with the following equation. U is equal to 1/2 mass times speed squared. So this, when we plug in our values together, so 1/2 times the mass that was given, which is the 167 times 10 to the negative 27 kilograms, times our speed, which is 2.50 times 10 to the 6 squared. And then we plug this into our calculator. I don't have a lot of storage, so I'm trying to do this quick. We get 5.22 times 10 to the negative 15 joules. And that is our answer for part C. Part D, what is the charge of the target nucleus? So for this, we're going to utilize the following formula. U is equal to our charge times our constant times our charges divided by the distance. So basically what we did in the first part, and we're going to start plugging things in. So we have our U, which is the 5.22 times 10 to the negative 15. We know our constant, 9 times 10 to the 9. And then we also know our charges because they were given. So 1.60 times 10 to the negative 19 times Q, which we don't know of, divided by the distance, which we do know, which is 529 times 10 to the negative 13. And then we get for our Q, and I've already done the calculations for this. We're going to actually rearrange this. We're going to move the 522 times 10 to the negative 15 here. 529 times 10 to the negative 13. 9, 10 to the 9. 60 times 10 to the negative 9. And now we're able to solve plugging this in our calculator. And our answer is 1.917 times 10 to the negative 18 coulombs. And that is our answer for part D. For part E, we have now 2 point charges are at fixed positions on the y-axis. We have our Q1, which is plus E at y equals 0, and Q2, which is equal to negative E at y equals A. Find the work you must do to bring a third charge, Q3, is equal to negative E from infinity to being at rest at y is equal to negative 2 A. All right. Let's see. For this, we're going to use the following formula. UI is equal to negative 1/4 pi Uriels. I have an issue pronouncing this, so I'm not going to pronounce it. E squared over A. And then what we're going to do here is basically just expand this a bit. So here would be Q1 times Q. I ran out of storage, but just to continue, Q1 times Q2 over R2 plus Q2 times Q3 over R23 plus Q3 times Q1 over R13. And this is equal to, actually this is UF. This is equal to 1/4 pi 1, oh, this is a 0. this is a 0, 0, okay, times negative e squared over a, I'm not even focusing the camera, plus e squared over 3 times a minus e squared over 2 times a, and this is equal to negative 7 e squared over 24 pi e a, and this is actually the answer for part F. I have it here as E, but the answer for part E is this formula right here, which is basically what we use to get to part F. I kind of forgot what part of the problem we were when my phone cut off, but this is the answer for part E, and this is part F. Okay, so part G states a point charge Q1 is equal to positive charge of 5 nanocoulombs is at the fixed position x equals 0, y equals 0, and z equals 0. You find that you must do 8.10 times 10 to the negative 6 joules of work to bring a second point charge from infinity to the position x equals positive charge of 4 centimeters, y equals 0, z equals 0. What is the value of the second charge? So what we're going to do here is utilize this formula for work is the second charge times V. So the potential at X due to Q1 is equal to our formula, work equals Q2. And here we're going to utilize this. We're going to plug this in for V. Oops. And then this, we're going to move this around a bit. We're going to solve for our Q2 charge in order to find it. So this would be Q2, work times X divided by K times Q1. And this is equal to our given 8.10 times 10 to the negative 6 times 4 times 10, excuse me, to the negative 2 divided by our constant, 9 times 10 to 9 to the 9th power, times 5 times 10 to the negative 9. And this is equal to, when we plug it in our calculator, and I already did, we get 7.2 times 10 to the negative 9 coulombs. And this is our answer for part G. For part H, this video is going to be so long, but for part H, the problem states, once the second charge is in place, how much additional work would you have to do to bring a third point charge? Q3 is equal to positive charge of 2 nanocoulombs from infinity to the position x equals 0, y equals positive charge of 3 centimeters, z equals 0. So what we're going to do is basically use this same formula that we use for part G, but it's going to be rearranged. So it's going to be Q times Q1 over Y plus, it's a similar one, not the same one, but it's sort of the same principle. So plus Q times K times Q2, or the second charge, divided by the square root of x squared plus y squared. So then what we're going to do is just plug our values in. Our constant value, which is 9 times 10 to the 9th power, times charge, 5 times 10 to the negative 9, divided by y, 0.03, plus constant again, 9 times 10 to the 9th power, times 7.2, the charge that we just found here, times 10 to the negative 9 power divided by the square root of 0.04 squared plus 0.03 squared. And this is all in the square root. So then this will be equal to, and I've already put this in my calculator again for saving time purposes. This is equal to 15 times 10 squared plus 12.96 times 10, not squared, to the second power, excuse me, to the second power. And then these two added equals to 27.96 times 10 to the second power. And then in order to get the work, we have to do Q3 times V, and this is equal to 2 times 10 to the negative 9 power times what we just found, 27.96 times 10 to the second power. And this will be equal to 5.59 times 10 to the negative 6 joules. And this is our answer for part H of homework 23 exam. Thank you.